Hi everyone. Today we're going to be continuing from the previous video of quadratic functions. So today we'll start by looking at the nature of roots, then we'll go to graphing quadratic functions. Okay, so the nature of roots. Now, generally, if I have to generalize it, right? So the roots of the quadratic equation or quadratic function, whatever you want to say, quadratic equation. And then I'm gonna specify it, right, of the quadratic equation. I'm always gonna most of the times I'm gonna talk about ax squared plus bx plus c form. So I'm gonna write ax squared plus bx plus c is equal to 0. This equation, right? It's given by like this. So it's given by the quadratic formula, which I'm sure you've learned in your middle school, is x equals minus b plus or minus the square root of. I'll just rewrite this part again. Square root of b squared minus 4ac, like this, all over 2a. Okay, so now the key part here, right, is understanding this part right here. So this, right? So the d, like in the previous video I mentioned, right, is capital D is b squared minus 4ac is called the discriminant, right? Called the discriminant. Discriminant. Okay, and the property of the discriminant is what we're going to look at right now. So okay, so I'm going to have 3 different cases for the discriminant. Okay, so I'm going to make a line here like this. So I'm going to have something like this. Okay, and I'm going to have my discriminant here. So my first case, right, like this. Okay, so I'm going to make the first case like this, right? It is if my discriminant is greater than 0. Okay, then I have real and distinct roots. Okay, so I'm going to have real and distinct. Okay, so real and distinct. That means I'm going to have 2 different roots. Okay, and they're going to be real roots, distinct. Okay, the second property, okay, is if my discriminant is equal to 0. Okay, that means I'm going to have real and equal. Okay, so I'm going to have only one roots, or you can basically say I have 2 roots which are the same. So technically I just have one root, right? Final. And you can probably guess it by now. It's going to be if my discriminant is negative, right? So when my discriminant is less than 0, right? When my discriminant is less than 0, I have complex roots. Complex roots. And you can probably tell, if you've watched my complex number videos, that basically when the square root of is when you have a square root of a negative number, you have the iota coming into play. So that's where you get complex numbers, thus complex roots. Right. So now if I have to explain this, with an example, a very simple example, what I can do is I'll change my color and I'll put an example right here, right? So I'll draw a line separating everything. I'm going to take an example, right? So my example is going to be a very simple one. I'm going to have x squared plus 2x plus 2 is equal to 0, right? Now, the only way, which I can see solving this, giving an appropriate solution to this is by using the quadratic formula. So I'm going to go ahead and use it. So I'm going to have x is equal to negative 2 plus or minus the square root of 4 minus 8 all upon 2. If I simplify this, I have minus 2 plus or minus square root of minus 4 upon 2. So now you can tell if I have a minus 1, right? So if I'll just do one more step right here, just so I'm refreshing everyone's memory. And if you haven't watched my complex number videos, so I'm going to have something like this: 2 times square root of minus 1 upon 2, right? Now I can replace this with square root of minus 1 is equal to iota, right? So I can replace it. I can make a simple, substitution. So I can write this as 2 iota upon 2, right? Simplifying it even more, I'm going to have 2 roots. I'm going to have minus 1 plus iota and 1 minus 1 minus iota. Okay, so these are my 2 final roots, okay, of my quadratic equation. Okay, now let's look at a very, out of the box question. Okay, so slightly different, very different. It's kind of out of the box, and I think it'll help, get your mind working of the different possible cases IB questions can ask you. So the question goes, if A, B, C are non-zero real numbers, then comment on the nature of the roots of the equations that's given right here, right? So now if we need to talk about, the nature of the roots, we can simply do that by looking at the discriminant, right? So that's what we're going to do. So we know discriminant is equal to b squared minus 4ac, right? So let's do that. So b squared would be minus 2a, right? So we have minus 2a whole squared minus 4 times a which is 1, right? And c is a squared minus b squared minus c squared, right? Now, when I expand this, I'm going to have 4a squared minus 4a squared plus 4b squared plus 4c squared. Okay, so I know my 4a squared minus 4a squared are going to cancel, so I'm going to have my discriminant as 4b squared plus 4c squared. Okay, factor out the 4, I'm going to get b squared plus c squared, and I don't think I can do anything more. So what can I say when after I have this, right? So let's look at this very closely. If it hasn't struck to you, let me explain this. Okay, so ignore the 4. Let's just look at b squared plus c squared, because this is a constant, right? We can ignore this. B squared plus c squared. We have two numbers which are being squared and added together, right? Well, we know that any number squared, whether it's a negative number or a positive number, always yields in a positive number, right? So we know this is positive. And we know this is also positive because the same thing applies for c as well. So now we have two positive numbers, right? So any two positive numbers, if we add them up, we're going to get a positive number, right? So we're going to get a positive number here. Therefore, we know that the discriminant is greater than 0. It's not even going to be equal to 0. Because why? Because we know they're non-zero real numbers right here. The condition is given, told us that it's a non-zero real number, right? So B and C are not zeros. There's some number, right? They can be negative as well, but negative 1 whole squared and negative 1 whole squared also gives us a positive number. So we know this is greater than 0. So now that they're greater than 0, what we can deduce, right? Oh, sorry. What we can deduce here, I can right here. So thus, the roots are real, right? They are real and distinct. Distinct, right? Roots are real. I'll rewrite this. And distinct. Real and distinct, right? That's what we had discussed previously, and that's what we're getting, right? Based on just by looking at the property of the discriminant. And you're going to believe it or not, you're going to have a lot of questions that, indirectly ask you to use the property of the discriminant. So it's very important that, you understand this as quickly as possible. Even if you have to spend, an hour more understanding it, it's okay. But just be sure that you understand how the discriminant works. Let's look at one more out of the box question. Let's look at this question. Let P and Q be a set of these numbers, right? So P and Q can hold 1, 2, 3, and 4, right? So the number of equations of the form px squared plus qx plus 1 having real roots is what, right? Trying to find the number of different equations that can be 4. Okay, so now to have real roots, right? The condition, again, trying to find the nature of the roots, right? So always, whenever we're dealing with the nature of roots, always remember discriminant comes into play. So I'll change the color, right? Whenever we have, real roots, right? Whenever we're dealing with nature of roots, right? Nature, right? Always go to discriminant. That should be like your key hit, right? Okay, nature, I'm talking about some nature of roots, whether it's real, imaginary, whatever. Always go to discriminant. Okay, so now, to have real roots, we know that the discriminant must be greater than or equal to 0, right? Now remember, if it's just greater than, it's going to have real and distinct. And if it's just equal to 0, right, then we're going to have just real roots, right? They're going to be the same roots, but real roots. They're not going to be distinct. So here they're just asking for real roots. So we can take both of them. That's why I'm going to say that discriminant must be greater than or equal to 0. So if I want the discriminant to be greater than or equal to 0, I'm going to do what? I'm going to do b squared minus 4ac, right? So b squared is what? Q squared minus 4 times p times 1 should be greater than or equal to 0. So I'm going to have q squared minus 4p should be greater than or equal to 0. Or if you want, you can also say q squared must be greater than or equal to 4p. Right? So this is the final relation that I have between q and p that must be satisfied from these numbers 1, 2, 3, and 4. Okay, so either I can use the first one or the second one doesn't matter, but I need to use either one of them. So this is how I'm going to go about it now. This is the easy part, right? If this was maybe seven mark question or six marks of a question, this would probably yield maybe 2 or 3 at max, right? The remaining of the question, the remaining of the points, 4 or 3, whatever they are, will depend on how well you can correlate this part of the question, right? And this is a slightly trickier part, right? So we have the values of P and Q that can be taken, right? 1, 2, 3, and 4. So now if we take, for example, let's take P is equal to 1, okay? So what are the different values we can have as Q, right? So Q can be, so if it's P is 1, that means this is going to be 4, right? So if P is 1, this is 4. That means Q squared must be greater than 4. And for what values can this be done? Well, if Q is 1, then we're going to have 1 squared is greater than 4. That's not true. So Q can't be 1. Let's look at 2. 2 squared, 4. 4 is greater than or equal to 4. That is good, so we can work. That's going to work. For 3, we're going to have 3 squared is greater than or equal to 4. Yes, it is. So we have 3 as well. What about 4? Yes, that also works. Okay? You can figure that out on your own. I don't think I need to explain that. Right? So 3 and 4, so 2, 3, and 4 work when P is 1. Okay, so now let's go for P is equal to 2. When P is equal to 2, the condition is only satisfied when Q is equal to 3 and 4. Again, I'm not going to explain. You can just plug the values in and see for yourself, right? If you want, I can explain this one more time. So if I take P is equal to 2, I'm going to have 8 here, right? So Q squared must be greater than or equal to 8. So that's only applicable when we have Q is equal to 3 and Q is equal to 4, right? That's what I'm trying to say this entire time, right? Now, if I have P is equal to 3, right, this is going to be 12. This part is 12, so Q must be 4, right? If P is equal to 4, I have 4 times 4, which is 16, right? So 16. Now, Q squared is greater than or equal to 16 only for 4, right? Because 16 is equal to 16. That satisfies the condition. So Q is equal to 4. So now, all we have to do is we just have to take the sum of all of these different values. So if we have 1, 2, 1, 3, 1, 4, which is 3, right? And then here we have 2, here we have 1, and here we have 1, right? So if I sum all of them up, right, I'm going to have total of 7 equations. 7 equations. That's my final answer. I can have total of 7 equations based on the values of P and Q I'm given. That's the answer to this question. All right, so now let's look at a few important results for the quadratic equation. All right, so the first one, right? So I'm going to discuss only 2 here. So the first one is if A, B, C are rational, okay? Are rational. And my discriminant is greater than 0, okay? But is not a perfect square, okay? But is not a perfect square. Perfect square is 16, 9, 4, right? Those are perfect squares. Is not a perfect square, right? Perfect square, right? Then the roots are conjugate surds of each other. Then the roots are conjugate surds. Okay, surds of each other. Of each other. Okay, so let's look at an example, right? So if I have an example of, again, x squared minus 2x minus 2 is equal to 0. Using the quadratic equation, what I'm going to get is 2 plus or minus the square root of 4 plus 8, right? Here my discriminant is, it's not a perfect square, right? Because 4 plus 8 is 12. And it's greater than 0, right? So it satisfies the condition, right? So here I'm going to have 2 plus or minus the square root of 12 by 2, right? So now what this means is conjugate surds, right? So when I simplify this a bit more, right? After simplifying it, just a second. So after simplifying it, what I'm going to get is 1 plus square root of 3 and 1 minus square root of 3. Okay? So these are the 2 roots that I'm going to get, right? So now if you see that very closely, you can see that they're almost the same, right? The only thing that differs is the minus sign right here. There's a plus sign here and there's a minus sign here. That's the only thing that's different. Now, again, this is kind of useful. Again, when you're given certain situations in IB exams, right? They're not going to directly tell you that the roots of the equations or something like that. They might tell you that you have it in the form of a plus b, something like this. A plus something. B root x, something like this, right? You have your roots in this form, so you're gonna have to back calculate basically, right, to get the equation, to get the values of a, b, and c. So this is when this comes super handy, to know that they're always going to be conjugate roots of each other, right? That's where you can use this logic and move forward and solve questions. Another property that I want to discuss here, right here, right, is I'm going to change the color, so I'll take green. And the second property is, it's very similar to this one again. So it's if A, B, C are real, right? Are real. But this time, discriminant is less than 0, right? Discriminant is negative, right? Then the roots are complex conjugates of each other. Complex conjugates of each other. Okay, example. I used this example again before as well. X squared plus 2x plus 2 is equal to 0. So the roots, the two roots that I get here is minus 1 plus I and minus 1 minus I. So if you remember from the complex videos, I clearly defined what a conjugate is. And as you can see, this also satisfies the condition of it being a conjugate. So again, this property and this property are very similar to each other, except the fact that you have complex numbers here and you have real numbers here. That is the only difference. But again, the application of both of them is quite similar, like this only. Where you're gonna have to back calculate and find the original values or the original polynomial or equation or something like that, something of that sort only. Let's continue with talking about graphs of quadratic functions. So a quadratic function can be expressed in different forms, but in all forms, all parameters are real numbers, and the parameter a, or the constant a, does not equal to 0. And this was something I even mentioned before in the first or the second video. Where I talked about if a is equal to 0, we're gonna have bx plus c, which is a linear function, right? Which defeats the purpose of talking about quadratic functions. So now I'm going to talk about 4 different ways of presenting a quadratic function. The first method, right, the first one right here, is called the standard form, right? So I'll change the color. Maybe I'll write it in gray. I'll call this the standard form. I don't call it, that's what it's called overall, right? Standard form. I'll just rewrite this really quickly. Standard. Okay, standard form. This is called the vertex form. Okay, so the vertex form, right? So obviously the standard form is our normal ax squared plus bx plus c. Now the vertex is slightly special. What we have done is we have used the method of completing the square, right? We have manipulated we have rearranged the constants and variables in such a way that we get a form like this, where our h and our k are the vertex of a parabola. Whether they're the highest point or the lowest point depends on a, right? If a is greater than 0 or if a is less than 0, right? A cannot be equal to 0, right? Very similar, it's this form also. This is also the vertex form. Okay, so this is also the vertex form, except here we're talking about proper variables in terms of a and b and c. Okay, here the capital D, right, is the discriminant. D is b squared minus 4ac. Okay, that's what my capital D is right here. So like this, right? That's what my discriminant is. So again, this and this are almost interchangeable, but I feel like this is a lot more useful if you're given, if you're given the equation in terms of ax squared plus bx plus c, and you're told to find the lowest point or the highest point in the parabola, then you go ahead and use this, right? Then you go ahead and use this. But if you have to, solve and show it, then you have to opt from equation number 2, right? These are all different types of equations. You will get used to them as you practice, right? And finally, I'm going to talk about equation 3, which is a normal, x minus p and x minus q, where p and q are our x-intercepts, right? We factor out a later out. First we make the factors and then we take a out. So we have x minus p and x minus q. Thus we can, deduce that thus we can deduce the roots of, or the x-intercepts of the function, right? So now if I have to, make a general graph of this, right? I'll change it back to white. So if I have to make, a general graph of my quadratic equation or my quadratic function, right? So I'll just draw the x-axis this way and then the y-axis this way, right? So I have my y here, right? And I have my x here, something like this. And maybe I want to draw a parabola like this, right? Something like this, like this. So this seems almost like this looks almost like a parabola, right? I'll change the color again. I'll take light blue. Okay. So this point right here. Okay. So this point right here, right, which enters wherever the parabola intersects with the y-axis is called the y-intercept, right? Or I can call it as 0, c, right? It's the exact c, which is found right here, ax squared plus bx plus c. And if you remember how to find your y-intercept, what you do is you just let x equal to 0. So f of 0 is equal to c, and thus I get my y-intercept, right? That's all there is, right? Here, right, this is my first x-intercept, this is my second x-intercept. I'm going to label this alpha and beta because these are my two roots of the equation, right? And then this is going to be my lowest point, my vertex, right? This is my vertex, so I'm going to label this as b by 2a and minus d by 4a, all right? I can label this as, h comma k if you want, but then what happened, you show the h comma k representing is that now you have more variables, right? You have more constants to deal with. You already had a, b, and c. Now you're going to introduce h and k. I mean, you can if you want, not an issue, but it just gets a little bit tedious in my mind, right? So this is my vertex, right? My vertex, right? And obviously this is my original graph, so I have y is equal to f of x, right? And which is basically ax squared plus bx plus c, right? And evidently a is greater than 0 because it's a concave up. If it's not that evident, I'm going to explain the concavity of the parabolas later on. So now let's look at a simple graph of y is equal to x squared, the very normal standard parabola, okay? Very normal, basic parabola, because that's we're going to make all the transitions from this standard equation, right? So graph of x squared. Okay, so I'm going to have on my parabola like this, right? Like this. So drop it down like this. So I'll draw, my x-axis like this, right? Just touching the parabola at 0, 0, right? Because that's where our normal parabola goes. So we have my x-axis, my y-axis like this, right? And I'll take it down as well. So just like this, right? So I have my equation, y is equal to f of x, right? Y is equal to f of x is equal to x squared, right? So now if I take different values of x and different values of y, I can plot basically my equation, right? So if I take minus 2, minus 1, 0, 1, 2, right? I'm going to get different values. So which I can, basically correspond with this curve right here. So I'm going to have 4, 1, 0, 1, 4, right? If I want to plot them, I can do that as well. So 0, comma 0 is right here. 1, comma 1 is here. Minus 1, comma 1 is here. 2, comma 4 is probably somewhere around here. Minus 2, comma 4 is probably somewhere around here. So like this, right? I have my normal parabola, right? Nothing too crazy, very simple. You just have to plug in the values, get an output, right? So now let's look at a certain property of location of vertex, right? So location of vertex. So here I'll change the color again. I'll take pink, right? So, or I'll just keep it as white, then I'll change the colors later on. So I have right here location of vertex right here. So I'm going to take three different equations in this case, okay? So my first equation, I'm going to put it in blue. I'm going to write it y is equal to x squared plus 1, right? Second equation I'll take in red, y is equal to x squared. And my third equation I'll take in green, which is y is equal to x squared minus 1, okay? Right? This is what I'm going to have. Now, I'm going to rearrange this equation, right? I'm going to make a small rearrangement, and I'm going to write it in the form of this right here. Y plus d by 4a is equal to a times x plus b by 2a whole square, okay? Because it's going to give me the vertex, right? That's what I'm trying to do. I'm trying to get the vertex. So if I try doing that, right? Because I can't really use h comma k form, because that's going to be really tedious, because I don't have a 2x, right? So if I want to do it that way, then I'm going to have to add and subtract 2x, and here I'm going to be left with a minus 2x or a plus 2x, something or the other left here. But here k is a constant. It's not in terms of x, so I can't really use this equation number 2, but I can use my equation number 4. And that's what I'm going to do right here. Okay, so what I'm going to do is here, I'm going to make a small transition, and the transition is going to be something like this. Okay, I'm going to bring the 1 to the other side, so I'm going to have y plus 1 like this is equal to x squared like this, right? Like that. Similarly, I'm going to do the same thing for the equation in blue. I'm going to have y minus 1, right, like this, is equal to x squared like this. Or if you want, I can put the squared sign, put the squared outside, right? So I'll have something like this. And I'll do the same thing for the green equation in green, right? So something like this. Like this. And this fits the equation that I previously had, right? So now, basically, I have my intercepts right here, right? So now if I want, I can elaborate this one more time, and I can write this as y plus 1 is equal to 1 times x minus 0 whole square, right? Similarly, I can make the same transition here as well, right? I can write y minus 1 is equal to 1 times x minus 0 whole square, right? So here my vertex is 0 comma 1, right? So my vertex is 0 comma 1, and here, right? Here my vertex is 0 comma minus 1, right? That is what I wanted to prove here, how you get the standard result. Now I could have, just said, it's a shift of plus 1 and minus 1, and then you can clearly see the vertex is going to increase and decrease. But the thing is, this is a very simple equation, right? It's a very, very simple equation. So it doesn't, really make sense for me to use that approach right here, because it won't work every time. This method that I've done right here, right, by creating a general form, will work every single time, no matter how complex the equation is, right? This will work every time. So now, if I have to, plot this, right? So I'll go ahead and plot it, and I'll show you the different parabolas that can come out of this. So I'll make a very small equation here like this. So my x-axis is right here, and then my y-axis is down like this, right? Like this. Okay. So my first is my normal parabola, which I'm going to make in red, right? So I'm going to have my normal parabola like this. Like this. I'm just going to shift this up like this, and I'm going to shift it up like that, so that my parabola looks pretty even, right? Now I'm going to draw the parabola in blue, right? The parabola in blue basically follows a normal parabola, right? The only difference is that it's shifted up by 1 unit, right? So I'm going to draw, maybe if this is my 0 comma 1 right here, so I'm going to draw the parabola from here. So it's going to look like this. essentially like this, right here. That's it, right? Now my parabola in green, it's going to be shifted down in the y-axis, right? Because the equation, it's a normal symmetrical parabola, but it's just shifted down to the vertex. So somewhere down here maybe, right? So now if I have to draw this like this, just like that. So this is what, location of vertex means, right? Basically my vertex, how it's shifted, but ideally, this could have been -1 comma 10, right? It doesn't matter, right? The principle or the concept is the same that's being followed here, right? Nothing changes, right? So this was basically, the location of my vertex, right? All right. So now let's look at, again, the location of vertex, but this time we're going to look at on the x-axis, right? So this was on the y-axis, right? Y-axis. Now let's look at the location of the vertex on the x-axis. All right. So now let's look at the location of the vertex through the x-axis. So I have the three different parabolas here. One is my standard parabola, y is equal to x squared, and then I'm going to talk about these different parabolas with respect to the one on the right. Right? So I have y is equal to x plus 1 whole squared, right? So if I want to, kind of rewrite this in the similar form, what I can do is I'll change it back to blue. So I'm going to have, something like y minus 0 is equal to x plus 1 whole squared. So here my vertex, right, it's going to be -1 comma 0, right? Or if you want, you could have even seen this in the form of x plus h whole squared times k, right? So you could have seen this as y is equal to 1, right? So 1 is always going to be there, right? So 1 times x plus 1 whole squared minus 0, where my h is -1 and my k is 0, right? Doesn't matter, it's the same thing. If you wanted to see it that way, you can also see it that way. Multiple ways of perception, right? Nothing is right, nothing's wrong. Whatever works for you, you can work with. You can use that, right? I just showed you both ways how you could have done it, right? Now, similarly, this is a standard parabola. We know the general shape of this. Now let's look at this one in green, right? So we have, again, I'm gonna use the first form because I liked it a little better. So I have y minus 0 is equal to 1 times x minus 1 whole squared. So here my vertex is 1 comma 0, like this, right? Similarly, you can say h is 1 and k is 0, right? It doesn't matter. One more way you could have seen it is, I guess, if this doesn't work for you, you could try maybe like this. I don't know if it will work for everyone, but just a suggestion. Maybe when y equals 0, right, my x is equal to -1, right? You can see it like this, right? Here, when y is 0, x is equal to just 1, right? I mean, if it helps at all, great. If it doesn't, I mean, I'm sure either of these methods should have helped you, right? So now let's look at graphing them, right? So if we graph these three parabolas, right? So again, I draw uh, my x-axis like this, and then my y-axis like this, right? Here x, and here's y. Oh my god. So here's my y. Okay, like this. Okay, so I'm going to draw the equation in red, which is my normal parabola, right? So something like this, right? This looks pretty accurate. I can live with it, right? Then I'm going to have a parabola in blue, right? The parabola in blue is basically has a vertex on -1 comma 0. So maybe like right here, I can say, right? My vertex is going to be right here. So my parabola will go something like this, right? Like this. Except I will just shift things a bit like this, like that, right? That'll be my parabola in blue. Now my parabola in green will be somewhere right here, right? So somewhere right here, I can have my vertex. So my equation will come out to be like this, like this. So these are the three different cases in the horizontal shift. Okay, so let's discuss the width of the graph, right? So I'm going to draw my xy plane very quickly right here. So my xy plane is right here, like this, right? Now I'm going to talk through this very intuitively, and then I'll give you a short trick to understand it. Now, if we plot take different points of x and plot them on the graph, right? We're going to have, maybe for x is equal to 1, we have y is equal to 2, right? For x is equal to 2, we're going to have y is equal to 8, and so on and so forth, right? So what happens is, and you can try plotting this on your own, right? So let me start with the red equation anyways, because it's a standard parabola. So my standard parabola is like this, right? Standard parabola, like this. Standard parabola is this. Now what's going to happen is, when you draw uh, the equation of the blue equation, I guess, right? What you're gonna have is, because of the 2, right? All the values of x squared, now it's gonna be being multiplied by 2. So you're gonna have a much steeper graph. Actually, you're gonna have a graph that goes like this. Okay, you're gonna have a graph that goes like this, right? And similarly, now if you look at the graph in green, right, everything, all the values of x squared, all the values of the equation in the red, y values, right, they're all being halved, right? So it's going to be a much wider graph like this, right? The graph is going to be much, much wider like this, right? Something of this sort, right? Not exactly, but you get the gist. If you want, you can go to Desmos and plot this on your own, right? You can put these equations and compare the width of how they fall out to be, right? Now, for example, the best way I can explain this. Now, if I take value of x is equal to 1, right? So x is equal to 1, right? For this equation, we're going to have y is equal to 2, y is equal to 1, and y is equal to half, right? So maybe if I take this as equal to 1, right? So I'm going to have right half here, something. Wait a second. So maybe like this, right? Something like this. So this is maybe 2, this is 1, and this is half, right? Something like this, right? That is what's going to happen with this width of the graph. Now, now if you want me to generally just summarize it, so what I can do is, I'll change the color first. All right. Basically, what happens here is, so if I have to generally summarize this, right? So what I can say is, basically, modulus of a, right? The greater the modulus of a is, right? Basically, a determines the concavity of the graph, or sorry, the width of the graph, I would say, right? So the greater the greater the modulus of a, right? Whether it's negative or positive doesn't matter. We're just talking about the width of it right now. The greater the value of modulus of a, right? Of a, right? The steeper or the narrower the parabola, right? Right? The smaller the modulus of a, the wider the parabola, right? That's all there is. That's all it is. All right, let's look at the orientation of the graph, right? So I'm going to have two graphs here, right? Y is equal to x squared and y is equal to minus x squared. So now if I have to plot them, right, my normal parabola is always in red. So like this, something like this, right? So I'm going to have my parabola like this, right? So touching the origin, obviously. And basically, now think of it, what's happening here is, right, all of the values of x squared, right? All the values of y are being negative, right? So there's just, all the y values will just be mirror images on the x-axis. So something like this, right? Something this, like this, right? Now, if you want to see it another way, you can see this maybe like, if this is f of x, right? Right? If this is y is equal to f of x, right? This is minus f of x, right? Or you can see that here in this part, right here, a is equal to 1 and here a is equal to -1. So the general statement we can make here is if a is greater than 0, we have concave up, right? And if a is less than 0, we have concave down, right? So here we have a greater than 0, here we have a less than 0. That's it, right? So now let's summarize all that we have done, right, so far, right? It's quite a bit of theoretical and conceptual information I've shared with you guys. So now let's, sum it all up, right? So let's call it important results, right? Important results. Important results. Okay, so now again, I'm gonna talk all of the results will be with respect to the equation of ax squared plus bx plus c, right? For y is equal to f of x, which is gonna be ax squared plus bx plus c, right? Change the color again, keep it peach, right? My first point, right, is that the graph between x and y, right? The graph between xy, right? Xy is always a parabola. Is always a parabola, right? Next is the coordinate of the vertex, right? The coordinate of the vertex are minus b by 2a and minus d by 4a, right? Where my d is my discriminant, which is b squared minus 4ac, right? Next point is when a is greater than 0, we have concave up, right? I just mentioned it. And when a is less than 0, we have concave down, right? Fourth point is the parabola intersects the y-axis at 0, c, right? So parabola intersects at 0, c. Intersects y-axis at 0, c. Intersects y-axis at 0, c. Okay? All right. The fifth and the final point says the x-coordinate of point of intersection of a parabola with x-axis are the real roots of the quadratic equation f of x is equal to 0. Hence, the parabola may or may not intersect the x-axis at real points. So essentially what it means is that if you have a parabola which intersects the x-axis, right, in two places, you're going to have two real roots. If it intersects only in one place, right, if it's tangent to the vertex, then it's only going to have one real root, right? And if it doesn't intersect with the x-axis at all, right, then it's not going to have real roots, or what it's going to have is imaginary roots, right? Because technically there are no real solutions to the quadratic equation. All right, so I'll stop the video. The video for here today. And in the next video, we're going to look at some a little bit more questions and a little bit more properties like signs of quadratic expressions and essentially understanding how the curve works, right? Or understanding how the graph works, right? Understanding when we have two real roots, or when when a is greater than 0, then what happens to the roots? What happens between the roots? What happens? What are the values of f of x between the roots, and what are the values of f of x after on the other side of the roots, right? Again, what I'm saying may probably make no sense to you right now because I'm not visually explaining it, right? But in the next video, we'll take a look at that, which will further, enhance or strengthen your conceptual understanding of polynomial functions and parabolas. So this was all for today's video, and I'll see you in the next one. Bye-bye.